Okay, let us start today's session. So, in this session, we'll discuss about the determinate beams, and also we'll solve some problems on the structure on the truss members. We'll be dealing mostly on the influence line diagrams. We'll solve some questions on influence line diagrams, both in the beams as well as in the trust members. So I am Prithvi. I am a PhD scholar from IIT Hyderabad. So let us start the session. So we'll start with a simple question first, and then we'll try to pick up and we'll try to solve a little more complicated questions. So the first question, we have a beam. So we have a cantilever beam. It's a prop cantilever with an internal hinge. This is a prop cantilever with an internal hinge. So let us say the hinge is about at the midspan of the beam. Sorry. So at the midspan of the beam, let us name it A, B, and C. So this is an internal hinge. All right. So the question is something like this. So the dead load of the beam, or the dead load of the beam is about 1.5 kilonewtons per meter, and the live load is about 10 kilonewtons. So this is a point load which is moving. Okay, so the live load is about 10 kilonewtons. So the question is, find maximum bending moment at support A, and also maximum shear force at hinge, that is B. Okay, this is the question. uh, so when we are dealing with the influence line diagrams, right, so mostly we'll be dealing with the live loads, right? So because the dead loads will not be moving, so influence line diagrams are like majorly we try to analyze the structures for the influence by using influence line diagrams only for a moving kind of a loads. So the dead loads is always constant; they remain on the structure. So the live loads are the ones which are really actually moving. So in the question it is given as the live load is about 10 kilonewtons. So let us solve this problem. Initially, uh, they are asking about the maximum bending moment at A, right? So let us just start solving the question. So we need maximum bending moment at A. So what we'll do is we'll just go from the basics. So we'll start a unit load, and we'll start moving it from let us say we'll start moving it from A to B and then to C. Then we'll find out what is the bending moment at A, uh, and then we'll instead of the unit load, we'll just uh, use the live load, which is given as 10 kilonewtons. So the live load, it is actually moving. This is 10 kilonewtons. It is moving from left to right or right to left, whatever it is. So let us solve this by, yeah. So I have the beam. This is point A. So first my unit load is here. 1 kilonewton is here, and this is B. Sorry. So this is B, and this is C, and this is A. So what happens to the moment at A because of this? So the moment at A is zero. Bending moment at A is zero because the load itself is acting at A. Next, let us have the same thing, and the live load is at position B. Okay. So what happens to the bending moment at A? So bending moment at A is nothing but it is phi, right? So you have one acting here. So this is trying to rotate this in this, so we'll have 5. Sorry, I didn't mention the. This is 5 meters and this is 5 meters. So the bending moment is 5 kilonewton meter. Okay. So parallelly, I'll just make one plot in which I'll try to draw the bending moment diagram. So initial at point A it is 0, at point B it is 5, at point C. So let me draw for point C. So we have the unit load at point C, acting at point C. So B is again a hinge. So what happens if the unit load is at point C? This is a very interesting situation. So you have one acting here. So one acting here. So what should happen? Actually, the bending moment at B should be 0. Bending moment at B should be 0. So for that it should be 0. You should have 1 kilonewton acting upwards. That means there is no force here. There is no bending moment or there is no shear force there. So again, the bending moment at A is 0. So again, that is 0. So this is my influence line diagram for bending moment at A. All right. So at A it is 0. At B it is 5 kilonewtons. At C it is 0 again. So this is linear. Let me draw it as a line. As a line. Okay. So how this is linear? Again, this is self-explanatory. You just place a load here, 1 kilonewton here. So you keep on moving this load. You'll have a linearly varying bending moment at A. Okay. So this is how we got it as a linear variation of the influence line diagram for bending moment at A. Okay. So we have the bending moment at A, that is the influence line diagram. So influence line diagrams are the bending moment diagrams at the place or the point of interest for a unit load which is traveling along the span, right? So right now in the question, the live load is mentioned as 10 kilonewtons, right? So for the 10 kilonewtons, what happens? So 10 kilonewtons. So live load is given as 10 kilonewtons, and we also have a dead load, so we should not forget about this. So the dead load is around 1.5 kilonewton per meter. So maybe this we can assume it as a self weight. So dead load is like 1.5 kilonewton per meter, and we have the beam. We have a propped cantilever beam. Sorry. Okay. So we have propped cantilever beam A, B, and C. Uh, the influence line diagram is something like this. Okay, this is at A, right? So this is at uh, what do we call? Yeah, this is bending moment influence ILD for bending moment at A. So this is phi. So yeah, so maximum bending moment. We need to find maximum bending moment. Maximum bending moment at A. So you just apply UDL. This is nothing but the dead load, which is constant, right? So irrespective of what you want, so that dead load doesn't move, right? So uh, the maximum bending moment at A will be again the first component is due to dead load. So due to dead load, it is, let us write it as component one. So due to dead load, it is half times, this is 10 meters, okay, and this is 5 kilonewton meter. So half times 5 times 10 times the total dead load, it is 1.5. Okay, and that is like 5 5 is 25. Okay, sorry, I didn't calculate this. 25 times 1.5. So it is about 37.5 kilonewton meter.
Now what is the
Now,
second
what is the second
component?
component? We also have a second component,
Due
that
to
is
live
due
load.
to live load.
So live
So
load is
live
what
load is what
makes an
makes an
impact,
impact
makes
or
an
makes an
significant
significant
difference
difference
in actually
in
assessing
actually
the
assessing the
maximum bending
maximum
moment at
bending
A,
moment at
because
A,
it
because
keeps
it
on
keeps on
changing its
changing its
position.
position, right?
So
So
at what
at what
position the
position
live
the li-
at what
at
position
what
we need to
position we
face
need to
the
face
live
the
load
live load
in such a
in
manner
such a
that
manner
we'll get
that we'll get
a
a
maximum bending
maximum
moment
bending
at A,
moment at A.
because it's
It's
obviously
obviously
the
the
ordinate, right?
ordinate, right? The
Maximum
maximum
ordinate.
ordinate here.
So
So
we need to
we
place
need
the
to
live
place the
load at
live load
B
at B
so that
so
we'll
that
have
we'll have
the
the
maximum bending
maximum bending
moment at
moment
A.
at A.
So
So
what is the
what is the
ordinate there?
ordinate there?
So the
So
live
the
load is
live load
10
is 10
kilonewtons.
kilonewtons.
The live
The
load is
live
10
load is 10
kilonewtons. The
kilonewtons and the
ordinate is
ordinate
5.
is 5.
So that is
So that
50
is 50
kilonewton meter.
kilonewton meter.
So this
So this
component comes
component
from
comes from
the
the
live load,
live load, due to the live load,
maximum bending
maximum
moment
bending
at A
moment
due
at
to the
A
live
due to
load.
the live load.
So put
So
together
put together,
bending moment
bending moment
maximum
maximum
is 50
is
plus
50 plus
37.5,
37.5, that
that
is
is
87.5
kilonewton meter.
kilonewton meter.
So
So
this will be the
this will be the
maximum bending
maximum
moment
bending
at A.
moment
So
at
that
edge.
is
So that
how
is
we
how we
design
design
the beams
the
for.
beams for, right? So we'll just see where is the maximum bending moment, and
Usually we'll
usually
try to
we'll try to
optimize as much
optimize
as
as much as
possible,
possible.
but in
In
case
case if it is
if
if
it
it
is
is
like
like
a
a but
in
in
most of
case
the
in most
cases
of the cases
we go for the
we go for the
maximum bending
maximum
moment,
bending
and
moment,
there
and
we
there we design the steel for, or
design
design
cross
the
sections
cross
for.
sections cross section for.
So
So
this is how
this is how
we find the
we'll find the
maximum
maximum
bending
bending
moment.
moment. And in this question, we
We can
can understand
understand
one
one
thing,
thing,
that
that the
the
maximum bending
maximum bending
moment
moment
is
uh, is
always a
always a
function of
function
live
of
load.
live load.
It's
So
not a
it's not
function
a
of
function
dead
of
load,
dead load,
because the
because the
dead
dead
load
load will
will
obviously
obviously
act on
act on
the
the structure.
structure.
So
So
that
that
is
is
not
not
going
going
to
to
make
make
a
a huge difference. So
difference.
when you have a moving live loads, so then that is where we see a significant difference in the maximum bending moment. So let us go to the same question. The same question we were asked to find out the maximum shear force at hinge B, right? So maximum
Shear force
shear
at
force at
hinge B,
hinge B,
how much?
how much?
So again
So again, we'll take the same question. So
mid
midspan we have a
hinge
hinge
A,
A,
B,
B,
and C.
and C.
So
So
in this again
we'll just
go
go
by the
from by the
basics. So
basics.
first
So first,
let us say
let us say
the
the
simultaneously I'll keep
simultaneously I'll keep
drawing
drawing the shear force diagram also.
the
Sorry, the
ILD.
ILD for the shear force.
So
So
yeah.
yeah. So in this, yeah, first case is we
We have
have
the
the
unit load
unit
for
load, or the
the unit
unit
load
load,
which
which
is
is
1
one kilonewton, which is
acting at the
acting at
support
the support
A.
A.
So
So
again,
again, what is the shear
shear
force
force
at
at B
B?
is
Shear
0
force at
because
B is zero, because
the
the
complete
complete
shear
shear
force
force
is
is
taken
taken
by
by
the uh,
uh,
the
the the
uh,
uh,
the support
the
at
support
A.
at A, right?
So
So
we will
we
not
will
have
not
any
have any shear force at B.
shear
So
force
shear
at
force
B
at
is
B is
0.
zero. I'm just
Denoting
denoting
it
it
as
as
0.
zero here.
So
So
again, we'll
again,
have the
we'll have
same
the
beam.
same beam.
Let us have
Let
the
us have
same
the
beam.
same beam. Okay.
So
So this is B,
and this is
and this
C.
is C.
This is
This
A.
is A.
Again,
Again,
for
okay.
this
For
time,
this time, let us have
uh, a unit
a
load
unit load
acting in the
acting
span
in the span
AB. So
AB.
what
So
happens
what
when it is
happens
in
when it is in
AB?
AB?
So what
So
happens
what happens in
in
that
that
case
case
is,
is
so
we
we
have
have
the bending
the
moment
bending
at
moment
B
at
should be
B should
0.
be zero,
One thing,
one thing,
and the bending
and the
moment
bending
at C
moment
should
at
be
C should
0,
be
sum
zero,
of
the
the
sum
bending
of the
moments,
bending
right?
moments, right?
So
So uh,
I'll take
I'll
the
take
bending
the
moment
bending
at
moments
B
at B
as 0.
as
So
zero.
in that
So
case,
in
what
that case, what
happens?
happens?
So
So we have,
let us
let
say,
us say,
yeah, this
yeah,
is
this
A,
is
B,
A,
and
B,
C.
and C, right?
So
So
I'll take it
I'll
as
take it as
RA,
RA,
and we
and
also
we
have
also have
moment at A,
moment at A,
and this is
and this is
RC.
RC.
So
So
RC
RC
times
times
this 5
this 5
should be 0,
should be
that means
0. That means
RC is
RC
0.
is 0.
So if
So if
RC is
RC
0,
is 0,
RA should
RA
take
should
complete
take
load,
complete
right?
load, right?
Because to
Because
have
to have
the
the
equilibrium,
equilibrium,
to have the equilibrium in
equilibrium in
vertical
vertical
direction.
direction, right?
So
So
we
we
have
should have
RA
RA
as
as
1
1
kilonewton.
kilonewton.
So
So
again, when you
again,
see
when you
that,
see
it's
that, it's
already
already
the
the
forces are
forces are
balanced in the
balanced
vertical
in the
direction.
vertical direction.
So
So
you don't
you
have
don't
any
have
shear
any
force
shear
at
force
B
at
again.
B again.
So
So even in that case, it is 0.
So
So I'll just place my unit load now at uh, just for the change of, we'll just change the pattern. So I'll just place my unit load at support C. So what happens again? So again, the support C offers a resistance and it is again 1 kilonewton. So the shear force at B is again 0. So it is again 0. So what is happening? So let me place my unit load at this time I'll just place my unit load at B itself. Okay. So I'll place my unit load at B. So I'm placing my unit load at B. This is my support C, A, B, and C. So let us analyze this. What is happening here? So when I place my unit load at B, uh, now yeah. So we have RC. Okay. We have RA, and we also have MA. Let us say. So RC times 0. This thing, right? So RC times 0 is again 0. So RC times 0 should be 0. That means RC, sorry, this is 5. So RC times 5 should be 0. So this is 0. So again, RA is 1. Okay. If RA is 1, what is happening at B? Obviously, if RA is 1, right? So this is trying to turn this hinge in this direction. So you should have a counter clockwise movement of 5 kilonewton meter. So that is what we have seen in the previous example. If you remember, when you are acting 1 here, you have a 5 kilonewton meter. I'll just show you. So when the load is at 1, so we have a moment of about 5 kilonewton meter, right? So that is what I'm mentioning. So this is 5 kilonewton meter. So we'll have 5 kilonewton over here. This is RA. Okay. So when you divide it, just left off it and just right off it, right? So how much is that? So just to the right. Okay. Yeah. So just at this point of time, sorry, at this point B, you have it as 1. Okay. So when you are placing it B exactly, let us say this is B. So this is 1. Now I just want to know what is happening at BC. What is happening when my unit load is at BC? So I'll place my unit load at BC, 1 kilonewtons. So what happens? Let us just analyze for that now. You have this, and this is my 1 kilonewton. This is C, A, B, and C. So what is going to happen here? So in this case, again, we'll just follow the same principle. So let us say this is RC. So RC is what the one is the one which I majorly majorly uh, of a concern, right? Because at B the moment should be 0. So RC times. So let us say this is at a distance of 2.5. That is half the span. So RC times 5 is 1 times 2.5. That means RC is almost 0.5. So if RC is 0.5, what should be the shear force at B? So B as a hinge again, a hinge cannot transfer the moment, but it can transfer the shear force, right? So hinge should have uh, uh, a shear force of zero point 0.5. So this is at half mid span, right? So this is at a half mid span. So half mid span, the shear force is zero point 0.5. At C it is 0. So this is something like this. Yeah. So let me draw it. Yeah. So it is something like this. So we have this is A, B, and C. So this is at B, B to C. The shear force at B to C is mostly actually the shear force at B is predominantly dominated when the live load is actually going from uh, B and C, which is in between the hinge and the roller support, right? So maximum. How do we find the maximum shear force? So again, we have first part that is due to
dead load.
dead load.
So
So
dead load
dead
is
load is again,
even if you
even if you
place
place
some part of the
some
dead
part of
load
the
in
dead load in
AB, that is
AB,
not
that
going
is
to
not going
matter
to
much.
matter much.
So the
So
only
the
part of the
only part
dead
of
load
the dead
which
load which
makes a huge
makes a
difference
huge
is
difference
uh, is in
is in
BC, right?
BC, right? So
Again,
again,
half
half
the area of
the
the
area of
triangle
the
is
triangle is
half into
half
5
into 5
times 1
times 1
times
times
the dead load
the
is
dead load is
1.5
1.5
kilonewton
kilonewton meter.
and
So how much is this? This is
2.5.
2.5.
So
So 2.5 times 1.5,
2.5
3.75
so
kilonewtons.
so what
So
happens
what happens
for the live
for
load?
the
So
live
where
load?
do we
So
need
where
to
do we
place the
need to
live
place
load
the
such
live
that
load
we'll
such
have
that
a
we'll have a
maximum shear
maximum
force?
shear force?
So again,
So again,
the
the
maximum
maximum
ordinate of
ordinate
the
of the
influence
influence
line
line
diagram
diagram
you
you
place
place
at
at
that
that
position
position
to have
to
a
have a
maximum
maximum shear force.
uh,
So I'll
live
place
load
my live load
at this
at
point,
this point,
that is
that
10
is 10
kilonewtons.
kilonewtons. So
Second part,
second part,
due to
due
live
to
load,
live load.
due to live
Due to
load
live
I
load, I
have
have
half
half, sorry,
10 times
10
1,
times
that is
1, that is
10
10
kilonewtons.
kilonewtons.
So
So
the
the
maximum
maximum
shear
shear
force
force
at
at
B
B
is
is
13.75
13.75
kilonewtons.
kilonewtons.
Okay.
Okay.
So
So
the maximum shear
the
force
maximum
at
shear
B is
force at B is
13.75,
13.75,
and
and
for the
for the
maximum
maximum shear force to be for
for the
the shear force to be
maximum at
maximum at
hinge B,
hinge B,
the live load
the
should be
live load
acting
should be
at
acting
B
at
itself.
B itself.
Whereas
Whereas
um,
um,
also
also for
for
the
the
maximum
maximum movement at
movement
A,
at A,
the shear
the
force
shear force or
the
the
live load should
live
be
load should
acting
be
at B.
acting at B.
So those
So
are the
those are the conclusions from this
question.
question.
And
And
also
also using the
we also
we
have
also
some
have some
tricks to find
tricks to
the
find the
maximum shear
maximum
force
shear
and
force and
influence line
influence line
diagrams
diagrams
for
for
bending moment
bending
and
moment and
shear
shear
force,
force,
right?
right?
So
So
what is
what is
that?
that? Let us just
Briefly
briefly
discuss
discuss
about it.
about it.
So in this
So in this
question,
question,
what was
what
asked?
was asked?
So we have
So
a
we
hinge
have a hinge here
and this is a roller.
and this is a roller.
So we are
So
asked
we
to
are
find
asked to
the
find
bending
the
moment
bending
at
moment
A.
at A.
How much should be
How
the
much
bending
should be the
moment at
bending
A?
moment at A?
So it is
So
very
it is
simple.
very simple.
If you are
If
asked
you
to
are asked
find
to
the
find the
bending
bending
moment
moment
at
at A,
A,
what
what
we'll
we'll
assume is we'll
assume
assume
a hinge
a
there
hinge there
and we'll
and
rotate
we'll
it
rotate
in such a
in
way
such
that
a
the
way
theta
that
is
the
1.
theta is 1. Okay.
So
So
what are we
what are
trying
we
to do?
trying to do?
What
So
I'll do
what I'll
is
do is
you are asked to
you're
find
asked to
the
find the
bending moment
bending moment at
at
this
this
position.
position.
So
So
you'll
you'll
just
rotate in such a
rotate
way
in
that
such
the
a way
theta
that
is
the
1.
theta is 1.
Okay.
Okay.
As this is
As
a
this is a
hinge,
hinge,
so this
so
can
this can
deflect
deflect
downwards.
downwards.
It can
It
also
can
rotate,
also
right?
rotate, right?
But this
But this
cannot move.
cannot move.
So
So this is
it
some
forms something like this.
it forms something like
So
this.
here the theta should
So
be 1.
here the theta should be 1.
So
So
theta is
theta is
what I mean
theta.
by
What I
theta
mean
is
by theta is tan theta. Okay,
tan
tan theta should be 1.
so 1
So
is only
1, it's only
possible if
possible if
this is 5
this is 5
and
and
this is
this
5
is 5
and this is
and
5.
this is 5.
Okay,
Okay,
this is one way
this
of
is one
finding
way of
out.
finding out.
And if you
And
want to
if you want
find
to find
in the
in
same
in the same
question,
question,
we are asked to
you are asked
find
to
the
find the
shear force at
shear
B.
force at B, right?
So this is
So this
A,
is A,
this is
this
B,
is B,
and this is C.
and this is C.
So for the shear
So for the
force,
shear force,
you just
you just
move your
move your the
point of
point of
interest,
interest,
uh,
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 assuming it
assuming it to
as a
as
roller
a roller
in that
in
direction.
that direction. Okay,
So you'll
so
just
you'll
move it
just
in this
move it in this
direction.
direction.
Again, as
Again,
it is
as it is
hinged,
hinged,
it can only
it
be
can
a
only
roller,
it is a roller,
right? So
right? So
it is
it is
pinned, but it
pinned,
can
but
go
it
in this
can
direction.
go in this direction.
So
So
you can
you
pull
can
this
pull
up.
this up.
Okay, you are
Okay,
just
you are just
trying to pull
trying
this
to
up
pull this up
by one.
by one.
What
What
happens?
happens? So
That will
this
deflect in
that
this
will
direction.
deflect in this direction.
So this is
So
one.
this is one.
These
So
are some of the
these are some of the
tricks
tricks usually
we
we
follow for
follow
doing
for
this.
doing this. So
I think
I think for the fixed
for the
for the
determinate
determinate
structures,
structures, yeah.
Why theta is assumed 1?
so
So
that
that
usually
usually
if you
if you
remember
remember
when
when
when we are
when
drawing
we are
the
drawing the free
shear force
shear force
diagram.
diagram, right?
So what
So what
happens
happens
when
when
the point
the
of
point
interest
of
is just
interest is
under
just
the
under
load,
the
we'll
load,
take it
we'll
as
take it
one,
as
right?
one, right?
Because
Because
you already
you
have
already have an
reaction
reaction
coming
coming
from
from
there.
there.
So
So
No, no, I'm
similarly,
asking
similarly,
about bending moment
correct,
diagram.
correct,
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 correct, yeah,
yeah.
yeah.
Theta.
So
So
even
even
when
when
you are
you're
plotting the
plotting
bending
the
moment
bending moment
diagram,
diagram,
so you
so
can
you
see
can see
that
that
that is
that
what
is
is
what it is
happening.
happening.
So
So
when you
when
are
you are
trying to
trying to
move your
move your
point
point
from A
from
to
A to
B,
B, So you are actually uh, you can see that you are rotating it by that, right? So in this equation you can see you are getting the maximum ordinate as 5. Okay. So not needed. For example, if you have something like 10 here, right? So this will not be this may not be theta 1, but here it is theta is 1.
No, but why we assume that theta is one?
We are not assuming it actually. So you keep on see you try to solve the problems, solve as many problems as possible. So you will get that trend, because for example for the shear force you are getting it as 1, right?
Yeah.
Similarly, when you try for the bending moment diagram, the bending moment diagram you need to shift in such a way that the theta will be 1, which obviously means that this should be equal to this.
Okay.
That is not assumption. It's not assumption. It is based on the results. So when you
Okay.
keep based on results we have worked backwards and we have found out that the theta wherever you want to find, right, it is always assumed to be tan theta. Not assumed, tan theta is found out to be 1. I hope it is clear now.
Yeah, yeah, yeah.
Yeah.
And is there any general rule now in this particular case
Yeah.
to identify that where the maximum bending moment will occur and where the maximum shear force will occur?
Uh, Again, we actually rule in the sense. See, right now in this maximum bending moment, it already in this question it is like a prop cantilever with an internal hinge, right? So
Yeah.
obviously the maximum bending moment will be at the support. I mean at cantilever I mean at the fixed support.
Okay.
So when you are dealing with multiple loads, multiple for example UDLs, or you have a moving UDLs, or you have a moving point loads, then there are some rules which we'll be discussing. We have some problems for that. We can
Okay.
discuss like where usually we will encounter maximum bending moment. That thing we call it as absolute maximum, because in inference line diagrams usually we'll try to pick a point and we'll say what is the maximum bending moment at that point. But when we want to find out the maximum bending moment all along the span, then we usually call it as an absolute maximum bending moment. So that we will see in the coming. We have some problems. We'll solve in that. We can see that.
Yeah.
Yeah. Okay. So let us go to the next question. So next question, again it is similar to that, but it is. Let me let me write down the question. So question two is, we have a cantilever beam, cantilever. So it's a simple overhang cantilever. I'm sorry, overhanged simply supported beam. So this is the beam. So we have this is A, B, and C. So we have a overhang beam. Uh, this is point D. This is only point. It's not an internal hinge. So point D. This is 1.5 and this is 1.5 and this is 1 meter. Okay. So yeah. So the dead load again, the dead load is again sulfate. So the sulfate of the beam is about how much is the sulfate? So the sulfate is found out to be okay. The sulfate is about 2 kilonewton meter per meter, and there is a live load which is 3 kilonewtons, which is going from left to right. Okay. So in this case, we are saying that the live load can move in. It can move from left to right, or it can also move from the right to left. Okay. So what is our, so assume this is fine. Maximum vertical support reactions at A. So maximum support reaction at A, first question, and also B. A comma B, and maximum moment in beam at D. This is D. So maximum moment at D. So let us solve this question. So now we will directly solve it. So what previously we are doing is we'll have a unit load. We'll place the unit load at the positions at various positions, and then we'll find out the influence line diagram for the shear force. So the maximum support reaction at A. So it's very very direct. So like I said in the previous one, how do we find the maximum shear force? So what we'll do is we'll just lift the beam by one one unit. Okay. So this is a hinge here, right? So sorry. Yeah. So this will be my so you remove the support. The process is if you want to find the shear force at a certain point, if it is a support, you remove the support and you lift it. You just lift that point by one unit and see the deformed shape of that beam. So this will be the deformed shape of the beam, right? If you lift it up, which is one. Otherwise, you can also you can also verify the same thing by using again the basic principles. You can place your unit load at A, you can place your unit load at B, D, B, and C. You can find out. So this is how it is. You can verify the same thing. So I'm just, for time being, I'm just taking it as uh, one here, and so this should be same. So what? So if this is one, how much is this? This is 3 meters. So this is 1 meter. So if this is one, this is three, and this should be 0.33. Okay, because one divided by three should be equal to 0.3 divided by one. That's what it is. Fine. So this is positive and this is negative. Okay. Again, in the shear force, I think it's the sign convention is of you know anyway it's a more significance, but at the end, however, we'll be giving it. We'll take actually we'll consider both the directions. So only in the bending moment we need to actually strictly follow the sign conventions because that actually says which side of the beam is actually in tension and which side of the beam is actually under the compression. Okay, so yeah, uh, this is my influence line diagram at A. Directly you need to put down so that the dead load is 2 kilonewtons. So you just add the entire area of the LD. So first one, shear force at A. First component is due to dead load. What is the entire area? 3 times 1 plus half times 0.3 times 1 multiplied by 2. So dead load is actually again if it is a UDL, it is nothing but series of point loads, right? Series of point loads. So series of point loads. So when you just integrate it, it is nothing but the area of it. So you find the area and then you need to just multiply it, multiply by 8. So what do you get? Uh, half and half can be 3 plus zero point 0.3, that is 3.3 kilonewtons. This is due to dead load alone. What about the live load? So where should I place the live load? So the live load should be placed where the ordinate is maximum. So the ordinate is maximum at A. It is one. The ordinate is one. So I'll just place there 3 times one, that is 3 kilonewtons. So put together maximum shear force at A is 6.3. Let me rephrase it. Is 6.3 kilonewtons. Now what about the maximum shear force at B? So what is the question? Shear force at maximum shear force at A and B. And what about at D? So what do we what shall we do? Yeah, what shall we do for D? So we'll have A, D, B, C. Okay, this is D, this is B, and this is C. So what I'll try to do is, uh, again, like we said earlier, we need to just remove the shear force at B. I mean, we need to remove the support, and we need to lift up, and we need to see what is the deformed shape of the beam. So I'll just remove this. I'll lift it up. So what happens? So this is a free support. This simply lifts along with it, and it will rotate here. Oh, sorry. This we can validate. Maybe I'll try to validate this one just for the sake of completion. So this I lift it up by 1 unit. So this is one. Then this will be again. You can see here. This is 3 meters, and this is 1 meter. So for 3 meters it is one. Then 1 meter it should be 0.33, right? So this should be 1.33. Anyways, we'll just validate this again, just for the sake of completion. So what I'll do is, this is my A, B, and C. A, B, C. So I want shear force at B. Initially, I'll place shear force at when I place my unit load at A, the shear force at B is zero. So yeah, this is the point. This is zero. Now next, I'll place my unit load at I'll place my unit load at D. Okay, I'll place my unit load at D. What happens to my shear force at B? Let me solve for that. So okay, this is my shear force. This is my shear force. So what happens? My shear force should be, I'll call it as X. X times 3 should be equal to 1 times 1.5. X is nothing but zero point 0.5. So this is my point. Okay, that is zero point 0.5. So when my unit load is at when my unit load is at B, what is my shear force? Shear force is again 1. So this is the point. Now when my unit load is at C, so when my unit load is at C, this is 1 kilonewtons. What is my shear force at B? So what happens? In this case, this is 1 times 4. Okay, that should be equal to X times 3. X is 4 by 3, that is 1.33. Yeah, so we kind of verified this rule that if you want to find shear force at any point, we need to lift that by unit length, or uh, unit displacement, and see the bending profile of it. Okay, see the deformed profile of it. So again, this is fine. So what about the maximum shear force? Maximum shear force at support B is, we have two components. One half times 4 times 1.33 times dead load. This is dead load plus I will place my live load at point C. So point C is 1 times 1.33. So this is 2, 4, 1.33, 1.33 times 4, sorry, plus 1.33. That comes to be, the turns to be 6.65 kilonewtons. This is my maximum bending moment, sorry, maximum shear force at B. So what is my other question? My other question is, what is the maximum moment at D? Okay. So for this, we'll just go by that principle which we have just discussed, and also we'll re-verify whether it's correct or not. Okay.
So
Yeah.
here for the A,
Yeah.
the other part should be minus, no, due to dead load.
Oh yeah, yeah, you're right. Sorry, I forgot to take. Yes, yeah. This is minus. So the 3 minus point 0.3. Huh?
Yeah.
Yeah, that should be minus. Yeah, this is 3 minus 2.7. plus 3 is again 5.7.
Yeah.
Yeah.
So yeah,
So
what
yeah,
about
what about
the bending
the
moment
bending
at
moment
D?
at B?
The bending
The
moment
bending
at
moment
D.
at D, sorry.
The
So
bending
the
moment
bending
at
moment
D
at D, this
is
is something like this, and this is something like this.
so
So
let us
let us
rotate.
rotate.
This is a
This is a
hinge,
hinge,
and I'll try
and I'll
to
try to rotate it.
try to
So I'll try
rotate
to
it.
rotate in such a way that
I'll
I'll
form
form,
okay.
okay, I'll form
The deform
the
shape.
deform shape. So the deform shape will be my
Influence line
influence line
diagram for
diagram
bending
for
moment
bending moment at that
position.
position. Okay.
So this is
So this
D.
is D.
Like I said,
Like I
I need
said,
to
I
rotate
need
it
to
by
rotate it by
uh,
uh,
unity.
unity, right? So yeah.
So first,
So
how
first,
much is
how
this?
much is this?
This is one
This is
meter.
1 meter.
All right.
All right.
So
So
yeah, how much
yeah,
is
how
this?
much is this?
This turns
This
out to
turns
be
out to be 1.5
1.5 meters.
meters.
1.5
1.5
meters.
meters, and this is also 1.5 meters.
So
So we'll just cross verify by using the
choose.
actual ones.
So we
So
have
we have A,
D,
D,
and this is
and this
C,
is B,
and this
and
is
this is
A,
C. A,
D,
D,
B, and
B,
C.
and C.
When my
When
unit
my
load
unit
is
load is
at
at
A,
A, the
the
bending
bending moment
moment
is
at D
zero,
is zero,
obviously.
obviously.
And
And
when
when
my
my
unit load
unit
is
load
B,
at B,
the bending
the
moment
bending
at
moment at
D is
D
zero.
is zero.
Yeah, that is
Yeah,
fine.
that is fine.
So
So this thing,
these
these things are
correct.
these are correct.
So
Okay, these seems to be correct.
what
So
about
what about when the unit load is at
this point?
this point?
Okay,
Okay,
when
when
the
the
unit
unit
load
load
is
is
at
at
point D.
point D.
So this
So
is
this is
one
1
kilonewton.
kilonewton.
When
So
this is
when this
one
is
kilonewton,
1 kilonewton,
this should be
this should be
sharing
sharing, right? This is
point
zero point
five,
0.5,
and
and this should be zero point 0.5.
so this is
So this
point
is zero
five
point 0.5
times
times
1.5.
1.5.
How much is
How
that?
much is that?
So point
So zero
five
point
times
0.5 times 1.5 is
1.5
about
is 15.
15.
So
Zero point 0.5 times 1.5. It's
0.75.
0.75.
So
So yeah, the bending moment should at
that
this
would be
point is
0.75.
0.75,
And
and when it is at C,
let me
let
place
me
my
place my
unit load at
unit load
C.
at C.
When it is
When
at
it is
C,
at C,
what
what
happens?
happens? So
We
we
have
have,
this
I'll
is
just remove this.
we
We
have
have
1
1
kilonewton.
kilonewton.
So 1
So 1
kilonewton
kilonewton, this is
1.33.
1.33.
Is it
Is it
1.33?
1.33? No. 1 times,
1.33.
let me just solve this.
So when
So
my
when my
bending moment
bending moment
is at
is
C,
at C,
we'll just
we'll just
RB
RB
times
times
3
3
is nothing
is
but
nothing but
1
1
times
times
4.
4.
RB is
RB is
1.33.
1.33. Yeah.
So this is
So this is
1.33,
1.33,
and you have a
and you have a
tensile
tensile
force.
force here.
Uh,
Uh,
that is
that is
1.33,
1.33,
and
and
yeah, this should
yeah,
be
this should be
0.33.
0.33.
So what is
So
bending
what is
moment
bending
at
moment
D?
at D?
Bending
Sorry,
moment
bending
at
Point
D.
moment.
point
Sorry,
five.
So
point 0.5.
point 0.5. Yeah.
Point
Yeah, this is
Yeah,
point
this is zero
0.5.
point 0.5.
Okay,
Okay.
if this is
If this
point,
is point, how much is
if this
this?
is
This is
0.76, we got
0.75.
it.
We got it right.
yeah.
Okay,
Okay. If this is
0.76, I
0.76,
think.
I think.
Yeah.
Yeah. So this is if.
Okay, we
Okay,
can't
we
say
can't
that.
say that.
Okay.
Okay.
In that
In that
case,
case,
all right.
all
So I
right. So
think we
I
can
think we
only
can only
qualitatively say
qualitatively
how
say
much is
how
the
much
bending
is the
moment.
bending moment. In this case, this is not working out to be the ones which we are thinking about it, right?
So
So
point seven five.
0.75,
Yeah.
yeah.
Okay. So
Okay,
we'll
so
have
we'll
a
have a
building.
building,
We'll have a
we'll have a
signing
signing
moment in
moment in
AB,
AB,
and
but
in
in
BC
BC
we'll
we'll
have a
have a
hogging
hogging
bending
bending
moment.
moment.
So yeah.
So yeah,
Uh,
uh,
okay. So
okay,
let's
let us
proceed
proceed.
to
So
maximum
maximum
bending
bending
moment
moment
at D.
at D.
So
So
you
you
just
just
find out the
find out
area
the
of
area
this,
of this,
area of
area
this.
of
So
this.
what
So
is that
what is
area?
that area?
Half
Half
3.75.
3.75.
Yeah.
Yeah,
Minus
minus
half
half
1.5
1.5
multiplied by 2,
multiplied by 2.
and I need to
And I
place
need to
my
place my
uh,
uh,
live load at
live load at
point D
point D
to get
to
my
get the
maximum,
maximum.
plus my
Plus
live
my
load is
live
how
load
much?
is how
This
much?
is
How
my
much is
live
my
load,
live load?
3
3.
3 times
3 times
0.75.
0.75.
This will
This
give
will
me
give
the
me the
maximum bending
maximum
moment
bending
at
moment at
D.
D.
Yeah.
Yeah.
And yes,
And yes, I want to correct. I think in this it is not how it is,
tan
right?
theta
Tan
is
theta
not
is
being
not
1.
being 1.
So
So
yeah, tan
yeah,
theta
tan
is
theta
what is
is
it?
what is
Tan
it?
theta
Tan
here
theta
it
here
is.
it is.
Yeah, it's
Yeah,
not
it's
1.
not 1.
It is 26.56.
Okay.
Okay.
It is
It's
not
almost 1.
45.
Yeah, it's
Yeah,
not
it's not
45.
45.
Yeah, maybe
Yeah,
I
maybe
think
I think we can.
anyways,
Anyways,
in this we can
qualitatively we can
understand what
understand
is
what
the
is the
bending
bending
moment
moment.
this thing.
This thing.
So
So let us go with that. I
shear
think
force
shear
will
force will
definitely
definitely
shear force
shear force
diagram will
diagram will
definitely give
definitely
us
give us some hint about
uh,
um, some hint about it. But I
bending
think
moment
bending
we
moment
can't
we can't
generalize by
generalize by
saying that
saying that the
theta should
theta should
be
be
the
the
rotation should
rotation should
be
be
1.
1.
Yeah.
Yeah.
Anyways, this is
Anyways,
the
this is the
answer for
answer for
this.
this.
We'll see now. We'll see some
Some
UDL,
UDL,
moving
moving
UDLs, and
UDLs and
moving point
moving
of
point of
train of
train of
loads.
loads.
Okay.
Okay,
So
so
we'll
we'll
have
have I have a question. Yeah.
so let
So
me
let
note
me
down
note
the
down the
question.
question.
This is
This is
question 3.
question 3. Yeah, let us take a simple problem.
So
So
this is
this
A
is
and B
A and
simply
B simply
supported.
supported.
The
The
span is
span is
10
10
meters.
meters.
The
The
span is
span
10
is 10
meters,
meters,
and
and
the
yeah,
span
the
is 10
span is 10
meters,
meters, and
we
we
have
have a
UDL,
UDL,
moving
moving
UDL,
UDL,
5
5
kilonewton
kilonewton
per
per
meter.
meter.
So the
So the
UDL
UDL
has a length
has a
of
length of
2
2
meters.
meters.
So
So
this
this
is
is
moving.
moving. Um,
Yeah. So
yeah.
what is
So
the
what is the
maximum shear
maximum
force
shear
at
force at
this point,
this point,
which is
which is at a distance of 4? Let us first solve
the
the
maximum shear
maximum
force at
shear force
some
at
given
some
point, and
given point,
also
and
we'll
also
solve
we'll
the
solve the absolute
maximum,
maximum shear,
absolute maximum
absolute
bending moment,
maximum
and
bending
also
moment,
the
and
shear
also the
force.
shear force. Okay.
So
So
this
this
is
is at
let us
let
say
us say
this
this
is
is C.
maximum
Maximum
shear force
shear force at C,
uh,
uh,
and
and
bending
bending
moment
moment at C, the
maximum.
maximum.
So
So
again,
again, what we can do, we can
for the shear
for the
force,
shear force we need to just
uh,
uh,
so
so
we'll just
we'll
take
just take
the
the
point at
point at
A,
A,
1
1
kilonewton.
kilonewton.
The shear
The
force
shear
at
force
C
at
is
C is
0.
0.
The shear
The
force
shear
at
force at
C
C
is 0.
is 0. So I'll just
And
simultaneously keep drawing. So
this
this
is
is my shear force diagram. So the shear force at C is 0.
next
Next,
when
when
my
my
unit load
unit load is at C,
when my
when my
unit load
unit
at
load at
1
C, 1
kilonewtons,
kilonewtons,
what
what
happens to my
happens to
shear
my
force?
shear
Shear
force?
force
Shear
will
force
be
will be,
this
this
is
is
1,
1,
then
then
this
this
should
should
be
be
1,
1. So this is
1 by
1
3,
by 3,
1 by
1
3
by 3
times
times
10,
10,
and 1
and
times
1
4.
times 4. No,
Let me solve
let
it.
me solve it. So
1 times
1
4
times
should be
4
equal
should
to
be equal to x. This is x,
x
x
times 10.
times 10.
X
So
should be
x should be
0.4,
zero point 0.4. So this is zero point 0.4.
and this should
And this
be
should be
zero point 0.6.
zero point 0.6. Okay. Just left to it, and also right.
Okay,
Okay.
so
So
we
we will have something like this. So we'll have
zero point
zero
0.6
point 0.6.
uh,
Yeah, zero point 0.6 here,
and
and
zero point
zero
0.6
point 0.6
at point
at
C. At
point C.
point
At
C it is
point
zero
C it is
point
zero
0.4.
point 0.4, right? This is
0.4.
zero point 0.4.
Let us take
Let us
one
take
point
1
over
point over
1
1
kilonewton
kilonewton just
to
to
understand.
understand.
So this
So
is
this
at
is at
distance
distance
2
2
meters.
meters. Let us take it 2
What
meters. What
happens?
happens?
So
So
2
2
meters
meters
will
will
have
have
x
x
times
times
10,
10.
that is
That
nothing
is
but
nothing
1
but
times
1
2.
times 2.
X is
X is
0.2.
0.2.
So at 2
So at 2
meters
meters it is 0.2.
at C
At
it is
C it is 0.4.
0.4, and
And
when it
when
when
it
it is
when it
going
is
from
going from
here to
here
here,
to
it
here,
should be
again it
1
should be
meter.
1 meter.
1
1,
meter
right? Complete
is a
is a
unity.
unity. So this is something like this. It looks like this. So yeah, something like this. Okay. So this is zero point 0.4.
This is
This is zero
point 2.
point 0.2.
This is
This
point
is zero
6,
point 0.6,
and this is
and this
0.
is 0. Yeah,
This is
this
0.
is 0.
Now
Now
where
where
do we
do we
need to
need to
place
place
our
our
UDL
UDL to
to get
get
the
a
maximum
maximum
shear
shear
force?
force?
So we need
So
to
we
just
need to
place
just
it
place
here
it here somewhere here,
because
because
here the
here the
ordinates are
ordinates are
lesser,
lesser,
right? In
right?
this
In
the
this the
ordinates are
ordinates
lesser.
are lesser.
So
So
you just
you
place
just
in this
place in this
and you
and
find
you
out the
find out the
area.
area.
So if
So
this is
if this
point
is zero
0.6,
point 0.6,
this is
this is
0,
0,
this
this
complete
complete
length is
length is
6
6
meters.
meters.
So this is
So this is zero
point
point
0.4.
0.4.
So
So
shear
shear
force
force
maximum
maximum
at C
at C
is
is
half
half
times
times
point
zero point
0.6
0.6
times
times, sorry,
half
half
times
times times
0.6
2
times
times zero point 0.6 plus zero point 0.4
times
times
5.
5.
And
This
this is
is 5,
5
5
kilonewton.
kilonewtons.
Okay.
Okay.
So
So yeah,
maximum shear
maximum shear
force
force
we are able
we
to
are
get
able to get
as 5
as 5
kilonewton.
kilonewtons.
Then
So there
you
is,
can't
you
if you
can't,
are
if you are
placing it
placing it
somewhere
somewhere
in this
in
span,
this span,
you will not get
you
the
will not
maximum
get the
shear
maximum
force.
shear force.
And if you are
And if you are
keeping
keeping
placing
placing
some
some
on
on
the left
the
of
left of
C and
C and
some part on
some
the right
part
of
on the
C,
right of C,
even
even then
then
you are not able to get, you are
you are
not
not
going to
going to
get
get
the
the maximum
maximum
shear
shear
force
force,
maximum
maximum
shear
shear
force
force
at
at
C.
C.
So the
So
only
the
way
only
is
way
to
is to
place
place
the
the
shear
shear
force,
force,
place the
moving live
live
load
load from
from
C to
C to
B,
B,
starting
starting
from
from
the
the
C.
C.
So
So
what
what
happens
happens
for the
for the
bending
bending
moment?
moment?
So let
So
us
let us
work out.
work out.
So
So
we have a
we have
beam,
a beam,
and the bending
and the
moment
bending
is
moment is
the bending
the
moment
bending
which
moment which
has to
has
be
to be, the bending moment at C
maximum.
has to be maximum.
So
So
A,
A,
B, and
B,
C.
and C.
So
So
uh,
uh,
how do I
how
need to
do I need
place
to
this
place this
such that
such
I'll
that
get a
I'll get a
maximum
maximum
bending
bending
moment at
moment
C?
at C?
So
So
you
you
already
already
know
know
the
the
uh,
uh,
ILD for
ILD for
the bending
the
moment
bending
at C,
moment
right?
at
The
C, right?
ILD
The ILD
for bending
for
moment at
bending
C
moment
is
at C is
something like
something
this.
like this. Sorry. So ILD for bending moment at C is
a
a
triangle,
triangle,
and
and
this
this
ordinate
ordinate is nothing but
4 times
4
6
times 6
divided by 10,
divided by 10.
that is
That is
2.4.
2.4.
So
So
this is
this
already
is
known.
already known. Okay.
So
So
uh,
uh,
so how do
so
we
how do we
uh,
find
the bending
the
moment,
bending moment at
the maximum
the
bending
maximum
moment?
bending moment? So
In this
in
case,
this
what
case, what usually what happens is that
we know
we
that
know that
the
the
maximum
maximum
area
area is actually in this is actually concentrated in this place, right, in this zone.
so we
So
have
we have
the
the
UDL of
UDL
length
of length
2
2
meters.
meters.
So
So what we'll do is we'll just place the UDL here,
and
and anyways we don't know how much uh, how how, how much of the part should
be in
be in
CB and how
CB
much
and
of
how
the
much of
part
the
should
part
be in
should be in
AC.
AC. That we'll try to derive it.
So let
So
us
let
say
us say
I am
I am
placing
placing
X
X
part in
part in
AC,
AC,
and this should
and
be
this
2
should be
minus
2
X
minus
because
X
the
because
total
the
part of
total part of
UDL
UDL
is
is 2.
the total
The
length of
total
the
length
UDL
of
is
the
2
UDL is
meters.
2 meters.
So if
So
this is
if this is
X,
X,
so this is
so this is
2.4.
2.4.
How much is
How
this
much is
going to
this
be?
going to be?
This is
This is
normal math.
normal math. So
The
the
slope of this
slope of
equation is going to
this
be how
equation. So
much
how
is
much is
going
this
to be?
going to be?
I'll call it
I'll
as
call it as
uh,
uh,
ordinate
ordinate
in
in
AC,
AC,
and I'll call
and
this as
I'll call this as ordinate
in
in
CB.
CB.
Okay.
Okay.
So
So
ordinate in
ordinate in
AC
AC is going to be
2.4
2.4
divided by
divided by
4, that is the
4, that is the
slope,
slope,
multiplied by
multiplied by
this length.
this length.
Okay, so
Okay,
that
so
length
that
is
length is going to be
4
4
minus x.
minus x.
So this is
So this
nothing
is
but
nothing but
0.6
0.6
times 4
times
minus
4
x.
minus x.
Okay.
Okay.
Now
Now
ordinate
ordinate
CB is going
CB
to
is
be
going to be
2.4
2.4
divided by
divided by the slope.
slope
The slope, actually, the slope is 2.4 by
6
6
times
times
this length.
this length.
Okay, how
Okay,
much is
how much
that
is that
length?
length? So that length is
6 minus
6
2
minus 2. Okay, let me write 6 minus
plus
2 plus x.
that is
That
zero
is
point
zero
0.4
point 0.4
times 4
times
plus
4
x.
plus x.
So this is
So
how
this
we
is, yeah, these
ordinate we are able
ordinates
to
we are
find.
able to find.
So
So
the
the
maximum bending
maximum
moment
bending
is
moment, right? So
already
what is the
given.
maximum bending moment?
So the
So the
maximum bending
maximum
moment
bending moment
is nothing
is
but
nothing
the
but the
area
area
half
half times
ordinate
ordinate
AC
AC
plus
plus
2.4
2.4
times
times
x
x
plus
plus
half
half times
ordinate
ordinate
CB
CB
plus
plus
2.4
2.4
times 2
times 2
minus
minus
x
x
times
times
how much is
how
this?
much is the UDL?
UDL is
UDL
5
is 5 kilonewton meter, 5,
5
5
kilonewton per
kilonewton per
meter.
meter, 5.
Okay.
So
This is my
this is my
expression for the
expression for the
maximum bending
maximum
moment.
bending moment. Okay,
So
so
I'll
I'll
just
just
substitute
substitute
0.6
0.6
times 4
times
minus
4
x
minus x
plus
plus
2.4
2.4
times x
times x
plus
plus
half times
half times
0
0
0.4
0.4
times
times,
sorry
sorry,
0.4 times
0.4 times
4 plus
4
x
plus x
plus
plus
2.4
2.4
times 2
times 2
minus x
minus x
times 5.
times 5. Okay, it's better. I'll just copy this. Yeah.
So you have this.
Anyways, I have this in my, yeah.
So
So
that is my
so that is my
expression for the
expression for
maximum
the
bending
maximum
moment.
bending moment. So how do we?
It
So
is again
it is again a
it is again a
polynomial, right? It's a
polynomial of
polynomial in degree
x
x
square
squared,
degree 2.
degree 2.
So
So
the
the
maximum will be
maximum will be
dm
dm by
dx
dx
should be
should
0.
be 0.
So what I'll
So
do
what
is
I'll do is d by dx of,
let me
let
take
me take
that
the,
that is
that
actually
is
solved to
actually
be
solved to
x
be
by
x
2
by 2
times
times
2.4
2.4
plus
plus
0.6 times
0.6 times
4
4
minus
minus
0.6 times
0.6
x
times x
plus
plus half
two
times
minus
2
x
minus x
times
times
2.4
2.4 plus
0.4
0.4 times
plus
4 plus
0.4x.
0.4x.
So you
So
take
you
the
just take the
integration
integration of sorry differentiation of this,
and
and what do you obtain? You will be
getting something
getting
like this.
something like this.
So
So
this will be
we'll
equal to
just further simplify it so that it will be easy for us to find the maximum bending moment also.
what
So
will
what
be
we'll be getting is
2.4
2.4
x
x
minus
minus
0.3x
0.3x
square
square
plus 2
plus 2
minus x
minus x
2 plus
2 plus
0.2x.
0.2x.
That is
So that is
equal
d
to
by dx of
you just
you just
simplify this.
simplify this. How much is this?
This is
This
nothing
is
but
nothing but minus
minus
0.5 x
0.5x
square
plus
plus zero
zero point
point 0.8
8x
x
plus 4.
plus 4.
What is d by
What is
dx
d by
of this?
dx of this?
It is nothing
It is
but
nothing but minus
x
x
minus
minus x
plus
plus zero
point
point 0.8
plus 0
plus
is equal
0
to
is
0.
equal to 0.
So x
So
is
x is
0.8.
zero point 0.8.
Okay.
Okay.
So
So
what does
what does
x
x
point 8
point
mean?
0.8
So
mean?
we
So
already
we
have
already
this.
have this.
So this
So
is the
this is the
beam.
beam.
So this is
So
where
this
we
is
need
where
to
we need to
find
find the maximum
bending moment.
bending moment.
So we have
So we have
assumed this
assumed
to
this
be
to be
x
x,
and this will
and
be
this will
2
be 2
minus
minus
x.
x.
If this is
If this is
4,
4,
this is
this
6
is 4,
and this is
and this
6.
is 6.
So x is
So
found
x
to
is
be
found to be
0.8.
0.8.
If
If
x is found to
x
be
is found to be
0.8,
0.8, that
then
means
we
you can
can
actually
take
make
one
one
conclusion
conclusion from it,
that
that
if you want to
if you want
find
to find
the
the
maximum bending
maximum
moment
bending
at
moment at
certain point
certain
B,
point B,
that
which
divides the
divides the
span
span
into
into
A
in
by
A
B,
by B.
okay, then
Okay, then so in
it
this
is dividing the
dividing the
span as
span as
4 by
4
6,
by 6, right?
the point
The
C.
point C.
So you need
So
to
you need
place
to
the
place the
UDL.
UDL
If it's
if
again
it's
lesser
again
than the
lesser than the
span,
span.
if the
If
length of
the
the
length of
UDL
the
is
UDL is
lesser
lesser
than the span
than the
itself,
span itself,
then
then
uh,
uh,
you place
you
the
place the
UDL in
UDL
such a
in
way
such a
that
way that
the
the
UDL is
UDL is
also
also
placed
placed
uh,
uh,
and the
and
point
the
is
point
actually
is actually
dividing the
dividing the
UDL
UDL
uh,
uh, uh,
uniformly.
uniformly. That
So the
means the
UDL
UDL
should
should
also
also
be
be
placed
placed
in
in
terms
terms
of
of 4 by
the
6. The
ratio
ratio
of the
of
UDL
the
should be
UDL
4
should
by
be 4
6.
by 6.
So in
So
this
in
case
this
it is
case, it is
0.8
0.8
by what is
by
the
what is
x
the
on this?
x
This
on
is
this is
1.2.
1.2.
That is
That
2
is
by
2
3.
by 3.
2 by 3.
2 by 3.
So
So what I'll just repeat
uh,
what I just said.
so if you
So
want to
if you want to
find
find
the bending
the
moment at
bending moment
C,
at C,
maximum
maximum
bending
bending
moment
moment
at C,
at C
due
due
to
to
the
the
moving
moving
UDL,
UDL,
we have to
you
place
have
the
to place
UDL
the
in such a
UDL in
way
such a
that
way that
the
the
UDL should
UDL
divide
should
that
divide that
point
point
as
as
A
A
by
by
B,
B,
where A
where
by
A by
B
B
is the
is the
ratio
ratio
of the
of the
span
span
AC
AC
to
to
CB.
CB.
Okay,
Okay, sorry, AC, yeah, AC to CB.
so
So
yeah,
yeah, so
right
now
now
right now
we
we
got
got
x equal to
x equal to
0.8
point
and
0.8,
y
and
is equal to
this is
1.2.
1.2.
So again
So
you
again,
just
you just
substitute in this
substitute in this
equation.
equation.
So my
So my
maximum bending
maximum
moment
bending moment
will be
will be
minus
minus
0.5
0.5
times
times
x
x. What is
square.
x?
X is
X is zero
0.8
point 0.8 square
plus
plus
zero
zero
point 8
point 0.8
times
times
zero
zero
point
point
0.8
0.8
plus
plus
4
4
times
times what is the
UDL.
UDL?
UDL is 5
UDL is 5
kilonewtons.
kilonewtons.
So this
So this
turns out to
turns out
be
to be
21.6
21.6
kilonewton meter.
kilonewton meter.
Okay.
Okay.
So this is
So
how
this is how we'll be
out
finding out
the maximum
the
bending
maximum
moment
bending moment
at a
at
certain
certain
location.
location.
So
So
similarly, if you
similarly,
want to
again, if you
find out
want to
the
find out the
absolute
absolute
maximum bending
maximum
moment
bending
in
moment
simply
in the simply
supported
supported
beam,
beam,
you already
you
know
already
that
know
the
that the
absolute
absolute
maximum bending
maximum bending
moment
moment
in
in
the
the simply
simply
supported
supported beam,
beam,
you need
you
to
need to first
draw the
draw the
ILD.
ILD, right?
The
So the
ILD is
ILD is
actually
actually something like this.
so
So
let us
let
say
us say
if this is
if this is
something,
something, So this is A and this is B. So the ILD of the bending moment diagram for a simply supported beam is AB by A plus B. So this ordinate should be maximum. Uh, when it is maximum, we can say that that gives us the maximum bending moment, right? So when this is maximum, so it is maximum when A equal to B equal to A plus B by 2, or that is nothing but the span by 2. So the maximum bending moment always occurs at the midspan. So at this span, when this is the midspan, this is nothing but the ordinate is AB by L. Again, AB is nothing but L by 2 by L by 2. So L by 2 by L by 2 by L. So that is L by 4. So if in this case, what do we need to do is, again, like we said, we know that the maximum bending moment happens in the midspan. So you place your UDL. In our case, it is 2 meters. You place the UDL in such a way that it also divides. I mean that the maximum point, the point C divides the UDL into half. Okay, so you'll place half here and you'll place half here. So that itself gives you the maximum bending moment. So if you find the area here, you'll get the absolute maximum bending moment. So this is about how do we find the maximum bending moment at a particular point or at a particular position in a simply supported beam for a moving UDL, and also what should be the maximum absolute maximum bending moment. So I hope this is clear. I think Vidyaji, I think you're able to understand this. You are able to follow this.
So one more thing what I noticed is
Yeah,
uh, that proportion what we got, that is point 0.8 and 1.2.
yeah.
It is actually ratio of the areas. So can we apply that?
Ratio of the areas. So yeah, that's what. See,
Hmm.
once we have this as constant, right? This is 2 point. Let us say this is constant. So the only thing which is changing is this length, right?
Yeah.
L1 and L2. So obviously the areas will also be proportionate because the ordinate is actually sharing the same length. I mean this is sharing the same one. So
Yeah.
yeah, obviously it is again indirectly it is nothing but the ratios of the areas. Yes.
Okay.
Yeah. We will in the next question we'll see how do we find the maximum bending moment and maximum bending moment for the train of loads.
Okay.
We'll have train of loads and we'll try to solve that. So this is question 4. Okay. And this is question. Yeah. I think I can solve. Start here itself. Yeah. The question is. Again, I've taken a very simple question, but we will have a train of loads here. So it is a simply supported beam AB. So it's a simply supported beam AB. The span is, yeah. So we have a train of load. Let me write the train of load first. Train of loads, something like this. This is 10, 20, and 30. 30 kilonewtons. So these are spaced. The first two are spaced at 2 meters apart. The other two are spaced at 3 meters apart. Okay. And yeah, the I think the span is 20 meters. So the span of the beam is 20 meters. So the span of the simply supported beam is 20 meters. We have a train of load which is passing along the beam. As you can see, there are three loads, 3 point loads: 10 kilonewtons, 20 kilonewtons, and 30 kilonewtons. So find absolute maximum bending moment. Okay. So again we know that the absolute maximum bending moment usually uh, in this point of load. Like, if you can just refer back to the lecture notes which the professor has covered, he actually derived one interesting point in that. So I'll just directly go through the process on how to actually find out the absolute maximum bending moment, because again the derivation is actually it takes a lot of time. So I'll just skip the derivation part, and I'll just show how do we take care of, or how do we go ahead and find out the maximum bending moment in terms of the uh, moving train of loads. So these are the loads which we have: one, two, three. So we have three moving loads we have. So what it says is that the maximum bending moment happens, or the maximum bending moment happens in such a way that you place 10 kilonewtons over here, and you have 20 kilonewtons over here, and you have 30 kilonewtons here, right? So you'll have a resultant force of all these um, train of loads, right? These train of point loads. So let us assume that you have a let us for time being, let us say that the resultant force is acting somewhere here. Okay. So again, what it was derived. Again, you can just follow the class notes to understand how it was derived. So uh, what it was said, or what it was derived, is that the maximum bending moment will happen under the load, under the point load, which is near to the midspan. So okay, it's near to the midspan, and it should be the maximum point load. That means that it should be the maximum. Uh, the load should be the maximum. Okay, so it should be near to the midspan, and it and the distance which is half the distance of this, which is half the distance of, let us say this is d. So this should be d by 2. Okay, I'll just rephrase. I know that I didn't explain it properly. So let us say we have a simply supported beam here. Okay, you have number of point loads. Let us say you have a lot of loads here coming. Okay, so you need to place your beam in such a way that, let us say this is the center. Okay, so you have the center C, or we call it as the midspan. So you have, this is midspan, this is L by 2. Okay, so it it happens under the load which is near to the midspan, and it is, let us say you have the resultant of all these forces at a distance d from the near support. Let us say this is the near support, distance d. Okay, so this happens, you need to place the force d in such a way that this is away from the midspan at a distance d by 2. That means the force, the next load, or the next maximum load should be placed from support A at a distance of L by 2 plus D by 2. So we'll solve the problem, we'll understand more clearly. So yeah, yes. So let us first solve the resultant force. Okay, so we have 10 10 kilonewtons, 20 kilonewtons, and 30 kilonewtons. So this is 3 and this is 2. So I'll just take the moment about this point as 0 and we can just find out the resultant. So what I'll do is 30 times 5 plus 20 times 2 is nothing but resultant. What is the resultant? I mean the force is 30 plus 20 plus 10, that is 60 times x. I don't know what is x. So x is nothing but uh, 30 times 5 plus 40 divided by 60, that is 150, 190 by 60. So this turns out to be 3.167 meters. So from where it is? From here, 3.167 meters from this support. So
So from 10, it is from 10.
yeah, sorry, yeah. So that is somewhere here, yeah. So this is 3.167 meters. So if this is 3.167, yeah. Now as we go ahead, what happens is that, so how much is this? This is 5 minus 1.6. 5 minus 3.167. This is 1.83. This is 1.83. So this is 1.83. So how do we need to place this? So we have the beam, simply supported beam. Okay. So we need to place this point, this which is 30 meters, 30 kilonewtons, which is the maximum. I'll also explain why the maximum should be placed under the consideration. So now this point, this should be the center of the beam, the center of the span. So if this is center of the span, this is nothing but half of it, right? So this is 1.88, sorry, 833 by 2. So what I'll do is, yeah, I'll just place my half. This is my half, okay, and here I'll have my 30 kilonewton coming, okay, and I have 20 coming here, somewhere 20 here, and we have 10 coming at this position. 10, 10, 10. So now what it says is the maximum will be at this point, okay. uh, the maximum is about that at this point. And how do you find the maximum? How do we calculate the maximum? So that is nothing but the ordinates. Okay, what is the ordinate? This will be, sorry, this will be AB by L. So what is AB? So this much is A and this is B. A is nothing but again L by 2 plus D by 2. What is L by 2? 10 plus 1.833 by 2. 0.9165. That is 10.9165. What about the other one? B. B is 20. 20 minus 10.9165. That is going to be 9.0835 meters. So what is AB by L? 9.0835 divided multiplied by 10.9165 divided by 20. Okay, that is going to be 4.95. This is 4.95 meters. Sorry, it's not. Sorry, there's no units here. It is 4.95. Now, how much is this ordinate going to be, and how much is this ordinate going to be? So if this is 4.95, I'll just divide it by, uh, I'll call it as O1 and O2. So O1 is going to be 4.95 divided by 10.9165 multiplied by, this is a tricky part. So this is 3 and this is 2 multiplied by 10.9165 minus 3, something like this. So this is going to be 4.95 divided by 10.9165 multiplied by 10.9165 minus 3. This is 3.5. Let me take 59. Yeah, 3.59. What about O2? O2 is going to be same thing, 4.95 divided by, let me write 4.95 divided by 10.9165, 10.9165 minus, how much is that, 5. That should be 10.9165 multiplied by 10.91, sorry, 10.9165 minus 5. That is going to be 2.68. So maximum bending moment due to the given train of loads will be 30 times 4.95 plus 20 times 3.59 plus 10 times 2.68. 30 times 4.95 plus 20 times 3.59 plus 10 times 2.68. Yeah, the answer is 247.1. 247.1 kilonewton meter. So in this we can see actually if it is under 30, right? So uh, the maximum load is 30. So when you actually have an maximum ordinate at that point, right? So you can actually enhance or you can have a higher value of bending moment. So that is the reason why we have taken the bending moment under the load 30. Considered bending moment under the load. So the location at which the 30 kilonewton is acting, right? So we have taken that section to have the maximum bending moment, and that is placed in such a way that the resultant force and the resultant which is from the point of interest should actually divide the beam, or the midspan of that should be the sorry, let me rephrase. So the point of interest is actually under 30 kilometer, right? So the point of interest and the resultant of all the point loads, the distance between both the point of interest and the resultant will divide the beam into half. That's what it means. So that is what we have taken, L by 2 plus D by 2. So yeah, any discussions, any queries in this?
No, what happens if it was 10, 20, and 20? How it will be placed?
So 10, 20 and
Or
20, 100.
you consider
Yeah,
30 heaviest load you have considered and divided the distance from the CG of the loads.
correct. So let us just see that also once. We'll just solve that. So we have you're saying 10, 20 and 20.
Yeah.
So what happens in this case? So let, you want the same spacing or you want some different spacing?
No, we'll try with same spacing.
Okay, so we'll have 2 meters and this is 3 meters. So 20 times 5 plus 20 times 2 divided by 50. So 140 divided by 50, 2.8. So
again it is
again, it is somewhere here.
this is
This is
2.8.
2.8.
Okay,
Okay.
you can
Again,
again
you can consider
this
this
as
as
midspan, and then you
midspan,
can
and then you can
find
find your
uh,
uh,
maximum
maximum
ordinate here.
ordinate here.
I'll tell you why.
I'll tell you why.
Because
Because
like if this is
like if this is
midspan,
midspan, right? What happens?
I'll just
We'll
draw
just
here.
draw the. See,
This is
this is
mostly based on
mostly
the
based
logic
on the
actually.
logic actually.
If you
If you
can
can
see,
see,
this
this
is
is
20
20 20
20.
20.
You have
You have your
resultant here.
resultant here.
So the
So the
resultant and this
resultant
should
and
be
this
at
should be at
midspan.
midspan.
So this should
So
be
this
more
should
than
be more than
midspan.
midspan.
Then this is
Then this
something
is
like
something
this.
like this, and this is something like this.
So
So
uh,
uh,
yeah, in this
yeah, in
case
this
what
case, what
happens?
happens?
Yeah, this is
Yeah,
one
this is
case
one
one.
case one.
This is
This is
ordinate one.
ordinate one.
How much is
How much is this? Is, let us say this is
ordinate two
ordinate two
and
and
this
this
is
is
ordinate
ordinate
three.
three.
So
So
ordinate one.
ordinate one.
Yeah,
Yeah, in
actually
this
you
actually
can
you can
do case one
do
and
case
case
one
two,
and
and then
case
you
two, and
can
then you
maybe
can maybe merge your answers, and then you can
take which is
take
the
which is the
maximum.
maximum.
So there is nothing
I,
like which is nearest to center of gravity of load. There is nothing correlation between that.
No, no.
no, no, no.
Actually,
Actually,
usually
usually,
again all
again,
these
all
things
these
actually
things
came
actually
up by
came up by
optimization
optimization
technique, right?
technique,
So
right? So
all these
all
things,
these things,
in
in
this
this,
it's
it's
not much
not much
mechanics
mechanics is
involved in this.
involved
It
in
is
this.
only
It is
about the
only about the
optimization.
optimization.
So we are
So we
trying
are
to
trying to
optimize the
optimize the
system. We are
system.
trying
We
to
are
find
trying
out
to
the
find out the
maximum
maximum
in the
in the
system, and then
system,
we
and
are
then we are
trying to find out
at
which
which
position we need to
position we need
place
to
the loads.
place the loads.
So this is
So this
again
is
you need
again
to
you need
do
to do
you need to find
find
case one,
case
case
one,
two,
case
and
two,
case
and
three
case
also
three
if you
also
have,
if you have some,
and then you
and
need to
then you
find
need
out
to
which
find
one
out
is
which one
giving
is
us the
giving us the
maximum
maximum
ones.
ones.
And
And like we discussed, this will help you
to
to
initially
initially
start
start
which
at
point
which
you are
point you are
getting the
getting the
maximum
maximum
ones.
ones.
So
So
you are
you are
100%
100%
sure
sure
that it
that it
is
is
on either
on
of
either of
20
20
under
under 20,
20,
but
but which
which
one
one
is
is
the
the
what
what
is
is
that
that
will
will
be
be
the
the
question.
question.
So
So in
in
this,
this
let us solve this. So you can see
we
we
got
got 2.8, right?
so this is
So this is
2.8.
2.8.
So
So
this is
this is
2.8,
2.8,
and
and
what is the
what is
rest?
the rest? 5. So this is 2.2.
So this
So
is
this is
2.2.
2.2.
So if this is
So if this is
2.2, this
2.2,
should be
this should be
1.1.
1.1.
So this is
So this is
1.1. So this is
1.1. This is
11.
11.
Uh,
Uh,
10 plus
10 plus
1.1,
1.1.
that is
That is
11.1
11.1 times
8.9
8.9
divided by
divided by
20.
20.
If we
If
consider
we
something
consider
else,
something else, so
O1
this
is going to
O1
be
is going
something
to
like
be
that.
something like that.
What
What
what if
what if you're considering
this point?
this
So this
point? So
point
this
will be
point will be
somewhere
somewhere. This is
2.8,
2.8,
and this is
and this
point
is
four.
point 0.4.
So this is
So this
point
is
four.
point 0.4. So this is
10
10
minus point
minus
four.
point
How
0.4.
much is
How
that?
much is that? 10,
10 minus point
10
four
minus
is
0.4 is 9.6. So
9.6
9.6
times
times
uh,
uh,
10.4
10.4
divided by
divided by
20. So
20.
which one
So
is
which one
greater?
is greater?
Obviously,
Obviously, I think
9.6 times
9.6 times 10.4 is 99. 99.84. This is 4.99 something. And this is 11.1 times 8.9
divided by
divided
20.
by 20.
This is
This is
4.93.
4.93.
Yeah,
Yeah,
this is going
this
to be
is going to
greater.
be
So if
greater.
you
So if you
consider this
consider
as your
this as your
point,
point,
again
again,
you also
you
have
also
10
have a
coming
10
there,
coming
right?
there, right? So
If you
if you
consider this
consider this
20,
20,
10,
10,
so this
so this
ordinate is
ordinate is
4.99,
4.99,
and this will
and this
be
will be
in terms
in
of
terms of
4.99 by
4.99 by
something,
something,
so on and
so
so
on
forth,
and so forth,
and this will
and
be
this will be
less than
less than uh,
4.99.
4.99.
So
So
yeah,
yeah,
anyways,
anyways, you need to do you need to find
case one
a
and
case
case
1
two,
and case 2, and from the case 1 and case 2 you need to conclude which one is giving you the maximum bidding moment.
Okay. Okay.
Yeah, yeah.
next question
Next
What
will
about
question will.
shear force
yeah.
Yeah.
in case of trains of loads? How to find the maximum shear force?
So shear
So
force is
shear force is
actually quite
actually
direct
quite
because
direct because,
for
for
example,
example, the
Or you
shear
can say
force.
support reaction.
yes,
Yes,
directly
directly. You
just
need to
lift the
just lift the
support up.
support up. For
For
example,
example,
the same question.
what
What
we'll
we'll
do
do
is
is we'll just
find the
find the
support. Let
support.
us say
Let us
this
say
is
this is
support,
support.
both
Both
the
the
supports.
supports.
Support
Support
reaction
reaction
for support
for support
reaction A is
reaction A
something
is
like
something
this.
like this, right?
So
So If in case in the question, or see, in reality it is always reversed, right? In reality all these things we usually come across in the bridges, right? Most predominantly, and also some kind of a storage systems, if you are moving the, if it is a godown or something, right? So we keep moving the loads or the dead weights, or you have some sorry, the loads, you keep storing them, so you keep moving from one grid or one slab to another slab. So again, that is
Uh,
very
yeah, I also encountered this in the case of gantry girders with multiple cranes.
correct. Actually, the previous question which I shared, right, that the 3 kN live load wala, that is actually a gantry girder. Yeah. Gantry girders in a storage go downs or something, where you're constantly moving the live loads. You need to take the live loads. You need to send it. You need to parcel them, and you'll get new incoming, or the new incoming loads to place inside, store inside. At the same time, you have bridges, a lot of things. Anyways, for the shear force, you need to just lift this up. Uh, Again, if in the question they are asking that the loads can be reversed, or uh, it is not only going from left to right, but it can also go from right to left or something like that, then you need to place the maximum here, and then smaller and you do iterations. So one or two iterations, case one, case two, you can directly find out the shear force, maximum shear force. The
There
only
must,
complication, yeah, sorry.
is there any relation with the now this is the influence line diagram what you're doing? And
Yeah.
should we place the maximum somewhere like that? What is the CG at
So
CG at support 8? Can it work
EV.
out that way? CG of the load.
No, CG actually in this. Uh, See, usually the reason why we have found out the CG in that, actually, if you go through the uh, what do you call, you if you go through the derivation of that, actually the derivation of that was well explained by the professor in the lecture. So you can see the CG actually, that for the movement the CG makes it influences, right? You need to have a CG, so you'll have a lever arm. So the maximum lever arm you have, the maximum movement it generates, right? So that is where the CG comes into the picture. But when it comes to the shear force, it is not much of the CG, but it is what's happening at the maximum ordinates. You can move it, you can keep moving, you can do one two trials, case one, case two, something like that, and then you can say it, under what loads. See, in this it is quite direct. You can place your 30 here, 20 here, and 10 here. So it is quite direct. So if you have otherwise also, for example, if you have by some means, maybe if it is a overhang beam, so what happens, you'll at some portions you'll have positive shear force, and at some portions you'll have a negative shear force, like we have seen in the previous question. So I think yeah, something like this. So in this case, what you will do is you'll just place your loads only in this. Even though if it is going inside, you will not place there. You will only place here. That is again more of a logic based. It's more of an optimized. You are trying to optimize the system.
Okay. So it is
Yeah.
basically on trial and error.
Correct. Yeah. These things. So this doesn't have CG or something like that, because in that CG will give us some clue, or some initial iteration, iteration zero, to actually find out what is the maximum point, or what is the optimized point at which we will find the maximum bending moment. Again, that is not the exact truth, right? Because we are trying to iterate. Because in the second question, like the ones which you asked me, in this it can either be on 20 left or 20 right. So we need to iterate. So at least that CG will give us the idea, exact idea, where it is, where it has to be located, at what point it has to be located.
Okay.
Yeah, we'll take one question on the truss, because usually most of the cases will find out the influence line diagrams for the truss members, because that is where a lot of loads coming, a lot of moving loads going, right? So we'll just solve one simple truss member, and then maybe we can wind up for today's session. So I just let me I just copy the question somewhere, man. So the question is 6 point. Yeah, so this is the question. I'll just take a fresh page. This is question 4, 5. Yeah, question 5. So this is question 5. So we have a truss. We have a truss. Yeah, we have a truss. So this is simply supported A, B, C, D, E, F, G, H. Yeah, so this is simply supported. Let us say this is span of, yeah, equal span. So this is equally spaced 6 meters, 6, 6, 6, and the height is 6 meters. So the question is find the force in member. This one, this diagonal. Let us directly solve complicated one directly. So find out the influence line, or yeah, draw the ILD for BG. Okay. So usually, if you see, you have two trusses. You actually have two trusses inside, one front and one on the back side. So these two trusses are actually supporting the bridge girder, or whatever it is, bridge, the beams, the girders of the bridge. So again, if you remember when we discussed about the truss members, analysis of the truss members, there are two important assumptions, or two important assumptions which we usually use for the analysis of trusses are that one is the truss members are connected to each other by a hinge connection, and the second one is the loads, whatever the loads may be, the loads always act as the nodes, right? So we'll try to find out the uh, total load, and we'll try to divide it proportionately to each nodes. So at the end, whenever we analyze for the truss, we always give the um, proportionate loads which we already analyzed coming from the girders. Above the girders, we have the live loads running over the girders, like maybe the train or a bus. So from that, we'll try to load our nodes, each nodes, and then we'll find out the forces in the truss members. So for this, again, this is a direct question. So in this, what it was asked is find out the influence line diagram at BG. So for this, we need to do the truss analysis. In the previous questions, we are actually having the static loads at some nodes, and then we are finding out the forces in the corresponding members. But in the ILD, it is nothing but as the load passes from A to E, how the forces are actually changing in BG. That is what the influence line diagram is, right? So in the first instant, okay, I'll keep drawing here itself because I don't. So when the force is at A, obviously there is no force in BG because the complete load is taken by the support. So let me just mention my. Yeah, I'll just draw BG something like this, and yeah, when the force is at A, my force in BG, or in fact, the force in all the members is zero. Okay, this is not actually zero. This is, I just want to mention. Yeah, right. So when my force is at, let me use the another some other color. So when my force is at B, right at B. So when my force is at B, what happens? So we'll just analyze it. So when my force is at B, okay, yeah, I'll take my support reactions here. Okay, I'll take this as my support reaction. So I need to do some analysis. So my my force is at B, that is 1 kilonewtons downwards. So 1 kilonewton downwards. So what is this? This will be, okay. Let me solve it. X times 24 is nothing but 1 times 18. So x is nothing but 18 by 24. 3 by 4. 3 by 4 is 0.75. So this turns out to be 0.75. And if that is 0.75, let me take area of what is it called, the method of sections. So let me draw it. So we have this something like this, and this. So here it is 1 kilonewton, and this is 0.75. So actually this is FBG, and this is what we need to find out. FHG, and this is FBC. So FBG, how do we need, how can we find this? So mm, fine, let me take the moment about this point. What is that point? G, at point G as 0 initially. Can I take that? Or no, I'll just take vertical equilibrium. That is quite straightforward. So 0.75 plus FBG, this is theta, and that is cos 45. Cos 45 minus 1 equal to 0. So FBG square root of 2, that is 1 minus 0.75, that is 0.25. So zero point 0.5 square root of 2. Zero point 0.5 times square root of 2. Point FBG is, how much is FBG? Sorry, it's not zero point 0.5, sorry, 0.25. 0.25 square root of 2 is 0.35. 0.353. Okay. So when the point load is at B, again, what is it? It is in tension, right? So tension, I'll just plot it on the top towards the positive side. Yeah, I'll place it on the positive side. So this is tension. So this ordinate is 0.353. 0.353. Now I'll take one more. Yeah, at E it is again 0. Okay. So there are two options. One, it can be something like this. One, it can be something like this. Or else there is another possibility. It can also be, it can go somewhere like this, and then 0 somewhere, and then it can come back to 0. So let's see what is the correct one. Okay. So we need to analyze for a few more cases to understand what is the correct answer is. So let us take at C. What happens when the load is at C? So when the load is at C, I'm just drawing directly now. So you have A, the load is at C, 1 kilonewton, and this is E. So this is C, and this is D, and this is B. So load is at C. What happens? So I'll take this part now. No, we can take, fine, whatever it is, fine. So if it is at C, then it is zero point 0.5. So if it is zero point 0.5, again I'll do the same thing. What happens is that uh, I'll just cut the beam. We'll do the same analysis, something like this. So in this case, in my next case, what happens is that this is going to be FBG, and this is going to be FBC, and this is going to be FHG. This is zero point 0.5. I don't have any load here, right? So F, this is at C, this is at D. F, sorry, this is F at B and this is at C.
FBG
FBG
cos
cos
45
45
plus point
plus
five
zero point
is 0.
0.5 is 0.
So
So
FBG
FBG is
minus point
minus zero
five
point 0.5
square root of 2.
square root of 2.
So this is
So this
zero
is
point 0.5
zero point
times
0.5 times
square root of 2.
square root of 2.
That is going
That
to
is going
be
to be minus
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 0.707.
0.707.
So minus
So minus
minus into
minus in that means it is
compression.
compression.
So yeah,
So yeah,
initially it is
initially it is
tension,
in
now it is
tension, now it is in compression. So I think yeah, we need to.
okay.
Okay, I
So this is
think
not
this
the
is
right
not
one.
the right one.
So this should
So
be
this should
the
be
right
the
one.
right one. So
Yeah,
yeah, where is it?
the C.
The C. Yeah, C.
Let me draw it
Let me
again.
draw it again.
So this is
So this
C
is C
minus
minus.
again at
Again,
E it
at
should be
E it should
0,
be 0,
right?
right?
You can
You
again
can
do
again do
one more
one more iteration
iteration,
at
but
D,
it is
but
going to
it is
be
going to be
linear.
linear because
Once it
once it
usually what
usually what
happens,
happens is that
diagonal
the diagonal
members
members
up,
up, it
it
actually
actually
it
undergoes
undergoes
stress
stress
reversals.
reversals.
So
So
it
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 it is in
it is
tension
in tension
at up to
at
some
up to some
extent,
extent,
some
up to
point,
some
and then
point,
it
and then
goes
it
into
goes into
compression.
compression.
So
So I'll just draw it here,
let me draw
something
it.
like this.
This can be
This can be
validated.
validated. You can
Diagonal
actually
members,
find out this D.
it's always
It's
linear.
always linear. So this
Follows the linear
follows the
path.
linear path.
So this is
So this is
0.707
0.707. This is
minus.
minus.
So this
So
should
this
be
should be
point seven zero seven by 2.
0.707 by
So
2.
that
So
is
that is
0.35
0.35.
and
35 times 2 is
353,
353, something like that.
and this is
And this is
0,
0.
and this is
And this is,
positive.
yeah, this is positive and this is negative.
So if you
So
are
if you
asked
are
to
asked
find,
to find,
or
like, or
if
if
we
we
are
are
asked
asked
to
to
find,
find
what
what
will
will
be
be
the
the
maximum
maximum
force
force
inside
inside
the
the
diagonal
diagonal
member
member or
BG,
diagonal
or
BG, or
for
for
what
what
load the
load the
diagonal
diagonal
member
member
BG has
BG
to be
has to be
designed.
designed.
So
So
usually
usually
when
when
we
we do the
if it is a
if it is
steel
a steel
member,
member,
we
we
check for
check for
both
both
the
the
tensile
tensile
loads
loads
and
and
also
also
the
the
compressive
compressive
loads,
loads,
right?
right? Because
Because
the compression
it also
it also
buckles.
buckles, right?
So
So
uh,
uh,
we'll see the
we'll see the
maximum
maximum
tension
tension
force,
force
and we'll
and
find
we'll
out
find out
what will be
what
the
will be the
maximum load,
maximum load.
and
And
for the
for the
for the
for the
given
given
cross
cross
section,
section,
we'll also
we'll
check
also
for the
check for
given
the given
maximum
maximum
compression, so
compression,
that
so that
whether
whether
it
it
is
is
going
going
to
to
take
take
that
that
load
load
or
or
not,
not, or
whether
whether
it
is
is
it
going
going
to
to
buckle,
buckle,
or
or
we
we
need
need
to
to
provide some
provide
kind
some
of
kind of
lacing
lacing
arrangements for
arrangements for
that
the diagonal
diagonal
members
members
or
or
not.
not. So
So
once
once
we
we
find
find
out
out
the,
the,
I'll
I'll
just
just
yeah, this is
yeah, this is yeah.
so once we
So
find
once we
out the
find out the
influence line
influence line
diagram for
diagram
any
for any
member,
member,
we can
we
find
can
out
find
what
out
are the
what are the
maximum
maximum
forces
forces
coming in
coming in
that
that
member
member
indirectly.
indirectly.
So this
So
is
this is
about
about
the
the
influence
influence
line
line
diagram
diagram
for
for
truss
trust
member.
member.
Similarly, we
Similarly, we
can
can
also
also
find
find
out
out
the
the influence line diagrams for
various
various other members of this trust actually,
and
and
then
then we can have a consolidate, or we can have a summary of it. Once we know uh, the intensity of the live loads, you need to just place them in an order, and or in that position, and you just need to multiply with that ordinate to find out the maximum, or to find out the maximum uh, the forces in it. So I hope this question is clear, I think.
Yeah, it's clear.
Yeah. So anything you want to discuss, because I can't start any other question now, because it's already we have only 10 more minutes.
So
So
it